Welcome to What is a Reward Function in Makya and Makya's design strategies. If you're wondering whether AI can really align with how chemists think and work, this is where we put that to test. We'll break down how reward functions let you tell the AI what good looks like, and how Makya's design strategy use the feedback to explore smarter, faster, and more relevant chemistry. No magic, no black box, just tools you can question, control, and push further. Our platform is unique. It harnesses AI that's driven by chemistry and guided by chemists to design synthesizable compounds, not just virtual ones. At the core is our generative AI, built for the de novo design of molecules that can actually be made. We don't stop at proposing structure. We integrate retrosynthesis technologies to find the best synthetic routes as well. Our approach goes beyond random generation. We aim to generate synthesizable molecules that accelerate the DMTA cycle. That's why we train on a dataset of 1 million building blocks and 2,000 named reactions. This chemistry-first approach expands our accessible space to 10 to the power of 27 molecules, unlocking massive diversity and novel scaffolds. From there, molecules can be optimized across multiple parameters, always in line with your project's constraints. Now, I want to emphasize something critical: user-defined control. At Ictus, we don't believe AI replaces chemists. We believe it empowers them. Human expertise defines the problem, sets the direction, and makes the final calls. The AI just brings speed and breadth you couldn't otherwise reach. And finally, our AI-driven retrosynthesis prioritizes molecules with realistic, efficient synthetic routes, taking into account cost, complexity, and what your team actually needs to make it work in the lab. We support a wide range of possible rewards. On the left, you have classical cheminformatics cores, like Tanimoto similarity to guide generation towards known chemical space, external scoring functions via API, and 3D shape similarity or pharmacophore alignments to ensure spatial relevance. On the right, you see more structure and target-specific approaches. Docking score, interaction fingerprints, and even predictive models train on your own data to guide the design towards likely success. The engine behind this is reinforcement learning, but what really matters is this: you define the rewards. Makya adapts. The system does not generate molecules in a vacuum. It generates molecules with purpose and with synthesis in mind. So, what exactly is a reward function in Makya? Think of it as the feedback loop that trains the AI to recognize what you care about, whether that's potency, docking score, pharmacophore, or any combination. These functions help detect undesirable properties early, guide the AI in refining structures, and prioritize the most promising candidates. On the left, you see what happened without optimization: raw generated molecules that might satisfy a few basic criteria but aren't aligned with your real world objectives. On the right, that's what happened when a reward function is applied. The AI focuses its generation on structures that better meet your defined goals, resulting in molecules that are more relevant, more efficient to optimize, and more likely to succeed downstream. Reward functions guides the AI towards the most promising chemical space for efficient optimization. You are not just generating molecule, you are shaping what the AI explore and controlling the trade-off it makes, just like a chemist would. Since we are talking about reward functions, there's a key point I want to emphasize. The more rewards you assign, the more constraints you are placing on the AI. In effect, you are giving it a longer to-do list, and the more boxes it has to tick, the harder it becomes to explore the chemical space freely. This can limit creativity and novelty. Instead of finding new interesting solution, the model might struggle just to satisfy all your criteria and end up generating nothing useful at all. That's why it's critical to strike the right balance. Use enough rewards to guide the model, but not so many that you shut down its ability to explore and innovate. If the generator fails to optimize everything you ask for, it might not be failing, it might just be over-constrained. Before we explore specific design strategies in Makya, let's start with this idea. There's no single path to designing better molecules. Makya gives you multiple ways to start from known ligand, hit, or scaffold, and then generate new synthesizable and optimized candidates. Whether you are trying to grow, refine, replace your molecule, Makya adapts to your design intent. From here, we'll walk through the different strategies that make that possible. Each one turned to support creativity, feasibility, and project-specific goals. Let's start with the simplest case, growing from a known fragment with one exit vector. This strategy is ideal when you have a core structure and want to explore what you can build off a single position. Here, Makya proposes molecules by growing in one direction, exploring variation while respecting synthetic feasibility. Now we increase the complexity, growing from two exit vectors. Instead of a linear expansion, you can grow in two directions, enabling more diverse shape and improved space exploration. This is especially useful when you want to maintain central interactions while modulating the periphery of the molecule. This strategy focuses on fragment linking, a powerful way to connect two non-motif or fragments into a single synthesizable molecule. Instead of growing out of your core, you are bridging two existing fragments. This is especially useful when you identify two regions of interest and want to combine them into a single, more potent or more efficient structure. Then there's macrocyclization. This strategy enables linking two parts of a molecule to form a macrocycle, which are structures that can significantly enhance stability, selectivity, and bioavailability. It's still rooted in real synthetic chemistry, but it expands the design space into topologies that are harder to reach with traditional methods. Finally, fine-tuning. This strategy focuses on small strategic modifications to existing molecules. It's ideal for late-stage optimizations or SAR refinement, adding or swapping functional groups, subtly adjusting property without disrupting the core structure. And across all this strategy, whether you're growing, linking, cyclizing, or refining, the goal is the same: to generate synthesizable, optimized, and diverse molecules starting from what you already know works.